Okay.
There we go.
So Isaac is going to be talking about outcrop expressions of polar layers that correspond to known SHARAD reflections in the North Polar layer deposits, NPLD.
Yeah.
Well, so go ahead and take it away.
It says my screen sharing is paused, so I'll resume. Is that, can you guys see my screen?
Yes.
Okay, great. I don't know why it says that it's paused. Okay, so thanks everybody for coming. I'm very excited to show this. I ran it past the SHARAD team and they were pretty enthusiastic also. So we've had SHARAD arrived at Mars in 2020, wow, 20 years ago, 2005. Started collecting data in like December 2005. So we've been collecting data almost 20 years. And immediately upon arrival, we noticed that there's a lot of reflections in the North Pole. And that was around the time we were starting to understand that the layers have a very nice climate signal. And also the layers are there's a lot of detail, but it's really hard to tease out the detail. And so one of the goals originally was, and there's been projects funded to do this, was to tie the layers that you observe with cameras to the radar layers, the reflections. And like I said, several studies have tried, and the best they can do is really say that there's some statistical frequency of the radar layers, reflectors with the observations from cameras, but they can't really do much more than that. And so, you know, we've been spending more than 10 years without really much advancement on here. So I'm really pleased to be able to show this. Okay, this is a high-res image from a spot. I'll show you more detail later. So this introduction to SHARAD. I'm not doing a lot with SHARAD today, but we've been looking at different reflections, and two in particular have been interesting to me. It's this turquoise one and the red one. And that's because the spiral troughs, the older generation of spiral troughs, seem to have formed sometime between the red.
Isaac?
Yeah.
Your screen is frozen. We're still seeing the high-rise image.
Oh, okay. Let's see. It says paused. I'll stop sharing and I'll try again. Thanks for letting me know. I don't want to get too far ahead. Okay. Is this any better? Can you see now?
Yeah, we can see you changing views and.
Okay, good.
Yeah, okay. You're good.
I'm trying to share just the window and not the full screen. Okay. So this was the image that I was talking about, the title screen. And this is the colors, the blue and the turquoise and red that I've been studying because I really care about what happened when the troughs formed. This was from a 2015 paper that I wrote with Jack Holt. And we noticed there were unconformities in the layers. So here's the blue and here's a blue unconformity, and the green is exposed in an unconformity in some places. This led to an idea that we go through climate cycles that we can detect with unconformities that represent periods of glaciation and interglacial periods. So there's two generations of trough. The oldest generation, most of the troughs had formed by the turquoise layer. I think, in fact, all of the older generation. And the second generation came after this green layer. So I really wanted to know, what do these look like? And there's places where they look like they could be exposed, but then when you go to look at them, they're not quite exposed, or it's really hard to get a bead on it and know exactly what you're looking at. So that's kind of where I left it. That was 10 years ago, and I didn't really think that I would ever find what I was looking for. So to give some context, the turquoise one I call R25. There's 26, 27, and sometimes there's a 28 that appears, and then 29 is the red layer. And I'm going to refer to them as 25 and 29 primarily. There's other layers that are interesting too that I'll bring up at the very end as a bonus. So this is that pattern, the 25 and 29 that I care about. There's like a larger space, a smaller space, and then a larger space or gaps between these reflections. And so anything that I see on the surface, I would expect to have similar gaps, that spacing. So after I started in 2008, so almost 20 years of looking, I finally found an outcrop where 25 and 29 show up. Unfortunately, the colors they don't match, but the blue, the 25, corresponds to the red layer there, and then the green is the 29. But I found a place where they come out, and it was a very unexpected place over here in this bottom right corner of the NPLD, somewhere around 20 degrees east. So I was very excited to see this, and I went and looked. And then you zoom in, and there's another one, R15, that I care about. And then there's this kind of blue here is R40. I'll get to at the very end. And I zoomed in. I said, oh, it might still be there. And I zoomed in some more, and I said, this might actually reach the surface. One thing for context is that the spatial resolution of SHARAD is about 470 meters horizontally. Vertically, it's around 20 meters vertical uncertainty. And so we can't pinpoint the exact place where these would come out, but that's okay because we're only moving a pixel or so. And so all I need to do is find a space within a pixel of that. Using our 3D data interpreter, I can get the exact location where they come out in X and Y, and then convert that to latitude, longitude. Here I'm going six significant figures, but I don't ever use that. I only use 3 significant figures because that's where JMARS cuts off. And 3 significant figures seems to be more than enough for 470 meter resolution. So I can convert this to latitude, longitude, and go to that exact spot. And so for that R15, the orange one, and R29, I convert, and I use my 3 decimal places, and I put a circle with 300 meter diameter on it. So this is using the crater counting tool. And this gives me a rough approximation of where the feature is, and it should be somewhere in there. It turns out it's actually almost dead center, which is really nice. R15 is an unconformity. You can kind of see it here. I'll show a better image in a second. Yeah. So here's an R15 unconformity that corresponds very nicely to this R15 unconformity that I've been mapping across the cap, and I showed it at LPSC. See my LPSC abstract for more details on R15. And I do have a couple more at the end. R29 would be within the circle, but it turns out to be almost exactly on this dark reflection, dark line. And I do the same thing for R25, and I get this. So R25 is this kind of irregular layer. R29 is extremely regular in thickness and in albedo. R15 is an unconformity. And then if I look at it from here, I can say, well, that's 26 and 27, and there's a 28 that sometimes appears, but then sometimes it goes away, which is the nature of 28. So that's pretty interesting. And if you notice, the spacing here between the R25 and 29 reflections happens to coincide very nicely with the spacing between the R25 and 29 layers that I've identified in HIRA. This is CTX. So I think that we might have identified outcrops of these radar reflections that would tell us a lot more detail about it. So R29 is what I previously called the trough initiation surface, and I was really interested in what it looked like. We were previously over here, and now we've shifted to the right, which is east. And you can see that you have the same spacing over here. In fact, it's probably even easier to see because this is due to the slope of the outcrop or the scarp there. The surface slopes range from 1 to 3 degrees. They're very low slope. And I haven't scaled this in any way except just to make the things line up. So I haven't moved any pixels around. And you can see that the 25 and 29 line up between the 2 different types of data sets. And obviously, the radar is not nearly as crisp as the CTX image. If I zoom in with high rise and get a better picture of what's going on, R29 appears to be this pretty uniform dark band that, and I just got a DTM this week. Thank you, Matt Chinaki and the high rise DTM team. I haven't had a chance to get the exact elevations, and I want to do that real soon. So here's the dark band. There's a potential 28 somewhere in there. 26 and 27 look very different. And then 25 is this kind of irregular layer that comes together, merges, and then separates, which is actually not too unexpected when you think about how windy it was at that time when the troughs were forming. So this is what I think those exact layers look like. And then you can zoom in some more and see it a little bit more detail. I hope the resolution is coming through. They look really crisp on my screen. So R27 seems to be this band of material. Now, don't get hung up on the albedo of the material. Several things we've learned in the last couple of decades is that the albedo doesn't tell you about the material composition. It may or may not include high dust. That depends on what we see, depends mostly on the lag and also the slope and aspect of the layer. And so this has a lot to do with the reflection from the sun bouncing off of whatever angle, more to do with that than the actual dust content of these layers. So don't get hung up necessarily that this is a brighter one and this is a darker one. This could be a prominent one, this could be a recessed one, and that could trigger what we see. Okay, After that, I attempted to find other sites with exposure of these layers. I went back to the 2015 paper and kept looking. And you might find a 29, but it's hard to find a 25. 25 is usually cut by the R15 layer. And I need to get my colors to be consistent. 2015 used to be green. I might make it green again. Anyway, so I looked here and I didn't find an exposure, part because it's been interacting with the trough migration processes. I went and did that with a bunch of them, and I found is that previously we were looking at site 1. I found a site 2 that's about 600 kilometers away. Alan Howard will be interested in this one because it's by Udza crater. The orange again is R15, turquoise 25, red is 29. The magenta is 35 and the blue is 40, and I'll get to those at the end. I want to zoom in, and I zoom in, I see that the 15 doesn't cut into the 25 here. So an exposure, we might see 15, 25, and 29 as an exposure. And I zoom in and I see this again. So often the 25 is cut and it's hard to identify. So I do the same thing where I get the X and Y of the radar, convert that to latitude, longitude, go to JMARS, and then make my little circles. And I think I found, so I'm not as convinced about site 25 as I am 29, but here's my R15 on conformity that's very easy to see. I think there's a 29 and 28, 27, 26, and even a 25 in here. 25 being more irregular. I recently got a high rise of this, and so this is the high rise image. The 26, 27 look actually pretty similar to what we saw elsewhere. The 25 is irregular. The 29 doesn't appear to be quite as obvious. It's not quite as obvious as in the other location. So here I am back to site 1, and I'm going to overlay the high rise I just got from site 2, and it's not too hard to line up what might be a 25 and a 26, 27, and a 29 right there. Same thing if I go over to the right, I might be able to line these up. And you know, the human eye can really play tricks on you. So I'm not saying this with certainty that they are, but it looks like a lot of the finely embedded layers also line up, not just the more prominent ones. And so I think that's a good indicator. So the finely embedded layers line up in both. So this is one that I would put forward, and then we're going to keep testing. Oh, and then here's that same high rise I just got from site 2 dropping on here, and so you can kind of see what I'm getting at, the way these layers are lined up. Okay. Oh yeah, and the other thing is you can play with it. You can shrink it and then try to make a different set line up, and you can do that too. So this is why I need to keep playing with it. But I think the original ones were the 26, 27 have the similar surface properties. These are the ones that I think I'm going to go with. And of course, there's more work to detail it. Okay, so here's site 1 with site 2 over the CTX overlay, and it looks really good if you overlay it this way. So site 1 on towards the east, it looks really good also. So that's what I said I want to go with, which is this one. Okay. And then I found a site 3 that's closer. So it's not 600, it's probably more like 400 kilometers away. This is a long way away. I found an exposure here, potentially. This is the original site 1, here's site 3. Convert the XY to latitude, longitude, zoom in, and it looks like it might outcrop. Here's a 25, 26, 27, and 29. So the 29 potentially is more prominent again. So I think site 3 is a really good correspondence, and site 2, I need to tease out the more details. So here's site 1, and I drop a site 2 on it, and you can see the 29 looks really good, 26, 27 look nice. Good correspondence between the finely embedded layers. The 25 has this irregular pattern, a slightly different irregular pattern, but looking good. If I look over on the right-hand side, it actually lines up pretty nicely. We have a nice thick space, the smaller spacing, and then the thicker spacing. Everything lines up really nicely here. So I think site 1 and site 3 correspond very well. I think site 1 and site 2 correspond pretty well, and I need to make sure I get everything, dot my I's and cross my T's. So here's my site 1 with my site 3 overlay zoomed in, and just everything lines up really nicely. And I'm really pleased with this correspondence here. So I'm going to go ahead and say that I believe that these are there, and I hope to have convinced you. Okay, what am I doing? Showing these again. So this is site 1 with site 2 overlay, and yeah, I think it's good, but I need to spend more time working on it to be certain for site 2. Okay, here's the site 3 zoomed in again. Everything really lines up very nicely for the site 1 and site 3. So I feel good about that. All right, here's some bonus material, and I'll leave a little bit of time for questions. I showed at LPSC my background with the wrap. The wrap is an unconformity that's up high in the stack, higher than that R15. And in my 2016 paper, we identified it as probably forming about 370,000 years ago based on this uptick. And this is modeling done by Levrard. But there's several other units there. This A unit I call R40, and Megan Russell and Aaron Russell are working on mapping that. The B I said was this internal layer corresponding to R29. Might change that now. And then there's actually an unconformity here that you can kind of tease out. If you look at the modeling, so there's Levrard in blue and there's Greva in black, and they take into account different things, but both of them show inflection points at about the same time. So Greva says that around 3 million years ago, you should have these major erosional periods where the ice is being transferred to the mid-latitudes. Around 1.8, you should get another one, and there's around this 0.6 or so, you should get another one. This is the one I said was the wrap. This one I'm going to call the major ablation and accumulation cycle, or MAC, and then this is the earliest major unconformity, EMU. The wrap, we can identify everywhere. This is mapped out in 2D and 3D. Aaron Russell did the 3D mapping. There's this major unconformity here that I like to call the MAC, massive ablation and accumulation cycle. My LPSC talk had a bunch of examples of this. It's all over if you look for it and you have the right 3D orientation that you can't get with 2D. It's a very impressive unconformity. I'd argue that this is better than most textbook examples of unconformity. If I found an exposure, now this is back towards that bottom right corner where we should see this R15 exposed. And we do, we have a very nice R15 here. And there's the early major one that I showed here as A. And I got to get all my colors straight. I realize here it's green, here it's green. And there's an unconformity in the high-rise image at this R40, which is the earliest major unconformity, and the MAC, which is the middle one. And when I go in and I tease out the details to figure out where the wrap is, I get this one. And so the colors don't match again, I'm sorry, but this would be the wrap, this would be the MAC, and this would be the EMU. All names pending except for wrap that's published. And there's an unconformity here. You can kind of see there's another unconformity here. And this one doesn't really show up as an unconformity. It's more of a disconformity in this location. So I think we've got surface exposures of the wrap, MAC, and EMU that tell us, and we haven't really found any other major unconformities. We found some local ones that are associated with trough migration. But here we have, I think, an exposure that contains each of the 3 major unconformities in the history of the NPLD. We might be able to start putting dates on these. And the beautiful thing is when you have bounding surfaces like these unconformities, it gets much easier to tease out the details of the layers. And so in this exposure, we don't have 25 and 29, but there is a 35, and I need to go out and figure out exactly which one that is. But at some point, I think what we're going to be able to do is put together a full stratigraphic column of the NPLD in radar and optical, and we'll have to do it piecemeal because no exposure with the optical cameras sees the entire NPLD, but the radar can tie different locations together to show it. And one of the cool things that I've found, and I'm not showing in this image, is below this 40, this EMU, there's very few reflectors. There's also very few optical layers. Most of the layers show up between and above, between 40 and 15, and then above 15. Okay, and yeah, so here we are looking at all of this together, and I changed the colors to match this time. And I think that's my last slide, and I got a few minutes for questions.
Hey, Isaac, it's Fritz.
Hey, Fritz.
Hey, really cool stuff. Could you go back to, I think, the previous slide? Yeah, that one.
This one.
This one, yeah. Let's see if I can, down in the lower left corner there, see where all the events kind of just disappear. And then you've got kind of so you've got above that. So the red, cyan, they
Oh,
just kind of go away, where you stop mapping them.
right.
And then you've got over to the right there, you've got some kind of angular events that cut across what you've mapped.
Yeah.
Yeah, the magenta one, you've got those angular events that, you stop mapping the magenta and then you've got some angled events in there. Do you have any
Oh,
idea what's going on, why you get the terminations there and
I
what those angled events are?
this to me looks like internal clutter that
Okay,
the 3D processor hasn't managed. There's a few other places where we see internal clutter.
right.
And of course, when there's internal clutter, that's the reason I haven't mapped the 35 across the magenta, because
Yeah,
there's interference with that. So to me, and Aaron Russell's seen this too, here's some of that internal clutter. I tend to
yeah,
just like ignore that in my head because I know that that's not real.
right.
Um,
Yeah,
so yeah, these features, we have to mitigate or just, gloss over in some sense.
okay. And then just where, you see a lot of what looks like kind of sweeping uh, imaging tails here where you stop mapping the like the cyan and
Mhm.
red units there. And so that I assume that that's kind of the same situation. You just can't
Yeah, so
continue across.
right, this is might be internal clutter as well. I see,
Yeah.
yeah, it's near the periphery, so there's going to be clutter from the surface also. Residual clutter seems like a possibility. Yeah, we're really close to not just this 40 or 50 kilometer thing, but we're actually really close if you go off to the side
Yeah.
in this track.
Just from an imaging standpoint, it'd be interesting to take a closer look at why those artifacts remain there and obscure
Yeah.
the layering.
Yeah, I'd be curious about that too. So I stopped the mapping, but also these layers sometimes fade in and out. The reflectors do. Like the green one here doesn't have that much interference, and you
Mhm.
can maybe pick a little more, and I probably should. But or this is Megan and Aaron, but they're still working on this layer, so that's not done. But they do fade in and out, so it's not just interference from
Yeah.
space clutter.
It looks like the magenta one is in there. You may have
Yeah,
more uncertainty about it because of the conflicting events, but looks
yeah, I
like
agree.
it does go across.
I bet you're right. This one's a pretty ubiquitous layer up until the point where there's truncations. Like here's a truncation.
Yeah,
There's
yeah,
plenty of places where there's truncations that got buried. So I need to go figure out where the unconformity is. Uh, I've highlighted it so it's not as obvious because of where I drew the line, but it's a really obvious unconformity in this image. You can see the unconformity nicely.
yeah.
And so
Well,
these are neighboring images. And this one unconformity is also pretty obvious.
yeah,
And so I know where the unconformities are on the radar. I know where they are in the optical. So it's just a matter of identifying exactly the spots.
right. One thing you might be able to do is, I don't know what the orientation of this arbitrary profile is, but you might be able to step kind of parallel to that and see how the interfering events change. And they may even disappear. So you may be able to get more confidence,
Right.
depending on what happens to that, about those layers that are uncertain.
Sure. Yeah, I can change the orientation. The orientation I've chosen is the one approximately right here.
Uh,
There's I
okay,
don't jetty, but I call it a jetty sometimes. So it's right there. And you can actually see in the black, which now I've highlighted purple for my more modern stuff. There's actually inconformities that are mapped out there.
right. Oh, cool.
I'd be curious if Alan or Oz have any questions. Oz has been thinking about this stuff, and I know Alan's been thinking about the layers a lot of his career. So I'm curious. Hey, Alan.
Well, I'm coming back to it after 20 years. But yeah, I'm working with Oz on what happens with regard to impact craters, older, younger. And we're presently looking at the Uja
Yeah.
crater. And I'm trying to understand and perhaps model. We'll see how far we get. What has been going on fairly recently in the Uja area. There's lots of unconformities there, and I presume it's the wrap layer. I sort of mapped some of the that it's the top unconformity. And it would seem to be somewhat a little more than 100 meters, maybe 130 meters on the average below the surface. Does that sound right for that part of uh, Mars?
Yeah, so the wrap I don't have marked here. One of the things, if you go back to Tanaka's '08 paper, he was suggesting that this PLD2, which is a really thin unit, was only tens of meters thick. That is what I consider the wrap unit. So above that last unconformity. And near the troughs, it is only a few tens of meters thick. But as you go in, it really gets up to like 130, I think is the thickest. So I would expect you might actually be looking at the MAC unconformity. If you're looking at this one, in the wrap one tends to be up really high, even in the frosty part. And there's only a few places I've found it where it's a true unconformity in the optical. With the radar, we see the unconformity in lots of places. So I would expect it to be higher up and maybe tens of meters thick at those exposures, similar to what Tanaka was mapping with PLD2. And then these unconformities, this one is the R15 or the MAC unconformity. And this, we're really close to UTSA. So like we're one trough north of UTSA right now. And this is I think it's in every single trough. You should see this one. And so it's the same age. And you can track it with the radar and show that these all connect. And that's what my LPSC talk was. And so if you're getting over 100 meters in this location, let's see, I would put that probably as the MAC. Wrap is up higher, so it's only tens of meters from the top. So, and if you're using the peak elevation in the plateau there, it's going to be somewhere in this upper section close to the frosty part. I'm really happy to, if you give me some coordinates, I can get you some radar profiles, or Aaron can do that.
Yeah, I think he's looking at some of that.
Yeah, hey, this is Oz. Yeah, really great stuff. I mean, the way the layers match up between SHARAD and visual and at sites 1 and 3 seem pretty, especially compelling. So like kudos on that. That's really great. I did sort of have a nitty-gritty question about site 2. And at the other sites, R29 was the prominent lower dark layer, it seemed like. But then at site 2, I think you classified that the darker looking bottommost layers are R28. And I was just curious, which you I think might have mentioned goes in and out at other places.
Yeah.
So I was just curious why here you felt it was 28 and not 29.
Yeah, good question. So when I'll go back up a step, R28 fades in and out within the radar. And to me, that's indicative of it getting too close to 29 to resolve fully. And then sometimes it's thicker, so we can resolve it. It's not a continuous radar reflection.
I see.
Here, yes, I need to refine this one. I was so excited I put the slides together, but probably I need to go spend a little more time with it. And like I even hinted at here, I've actually got some uncertainty if it's this or this. So this is site 2 on top of site 1.
Right.
And yeah, so this could be 25 that gets right under this unconformity. And then it would be a more darker layer for 29, or it could be this, which is what I originally marked.
Right. Okay, gotcha.
And this one that doesn't match up quite as nicely. And so I need to keep doing some work on this one. I really need to just go back and get the exact locations again. Like if I put it this way, it looks really convincing to me.
Mhm.
right about there. And so in that case, maybe 29 is the dark band, and what's below that is, so then 28 wouldn't really be as prominent. In fact,
Right.
oh, can I group these? This is locked. In fact, I might have just convinced myself that this is the way it has to be. Sometimes you do stuff.
Right. Right. Yeah. No, it helps just to talk it through.
In that case, 29 would be the darker one. 26 and 27 line up kind of well on this, actually
Okay.
pretty well. And then 25 would be this guy. I don't know.
Right.
I might be able to convince myself on this one, but site 1 and site 3, I feel really convinced about.
Yeah.
So showing that, and this one is a tentative one.
Yeah. No, I agree that those both look great and very convincing. And the sort of then I kind of have a more general question, which is, I don't know if you can conclude anything, but I guess like just what are your thoughts on what, like looking at this and then looking at, like what does the SHARAD layer represent? Like looking at where you have the R25 and the arrow,
Yeah.
is it just the middle layer? Or is it the two layers around sandwiching it? Is that part of the layer
Oh,
set? You know what I mean? That you see in a SHARAD.
yeah.
Just curious about that. Like if
Right.
you have any insight into it,
Yeah. So in this case, R25. So when I zoom out in CTX, it actually becomes more regular. And here it's a little bit less regular.
Mm-hmm.
Don't know what's causing it, the top or the bottom or the middle. I don't. R29 looks to be a discrete unit or discrete facies that
Okay.
create it. So then you would be going potentially from ice rich to dust rich to ice rich. And that'd be interesting because then if it's dust rich and it's receding faster, that actually matches a hypothesis that I've got in review right now. This opposite of where people were suggesting that the dust rich layers are more prominent. So it'd be reversed from that hypothesis.
Interesting.
I think I can generalize and say one thing though.
Uh-huh.
The finely bedded layers, people have been saying, finely bedded layers can also create constructive interference to give you a reflection. I think
Right.
that is not happening in the NPLD. I don't, from this section, which is like 100 something meters thick, I don't see any evidence that the finely bedded layers are creating reflections. It's more of the discrete layers. Because there's a lot of finely bedded layers in here. I don't see anything associated with them.
Right. And just the one more quick follow-up for R29, which seems so sharp, I guess, relative to, the other ones,
Yeah.
the visual images. Is there anything in the radar that suggests it's also more discrete, like in terms of the intensity of the reflection or whatever?
Not here. So this is just one location.
Right. Right.
The one thing I liked about 25 and 29 is, besides the fact that the troughs were forming and fully finished by 25, is that they're really easy to recognize because of this pattern, because the spacing. But also, I don't think that 29 is brighter. 25 looks brighter here, but in other places 29 is brighter.
Yeah.
29 is more ubiquitous than 25 because it was lower, so it didn't get, when there were ablation periods, 25 was lost, but 29 wasn't.
Gotcha.
But I can't say for sure that it's brighter. Like over here, 29 looks brighter to me than 25. And over here, 25 is brighter. So I can't say for sure. It might be
It's nothing consistent. Yeah.
Yeah.
Right.
I wish I could. Well, I'll give you more details. But I think we're finally advancing on a story where we can put discrete reflections next to discrete, at least sections. And I'm really excited about that. And so
Yeah.
we might be able to put together a full NPLD section. I'm working with Kevin Lewis and Oded Aronson on several sections, and so we might be able to piece together the whole thing with an MDAP or something. Norbert, I see your hand is up. Thank you for your patience.
Yes, so will we ever get volumes for these big layers? I mean, the total mass moved to the North Pole, right? The total ice mass is the most important constraints we'll get on the Martian ice age cycle anytime soon. So any chance we'll actually get volumes for these big layers?
Yes, we're working. We have an MDAP funded. Matt Perry's the PI. Aaron's a co-I. I am being funded to help do this work. So currently I'm mapping 25. I've got 60 to 70% of that done. That was my LPSC talk, so I didn't show it all here. I actually probably have it opened. and I've done much more. This is 3-month-old mapping, but so I've got a lot more area, and we're going to have the volume after the MAC, between the MAC and the wrap unconformities. We have the volume already above the MAC, sorry, above the wrap. So let me, yeah, I can tell you the volume after this unconformity. I'm about to be able to tell you the volume between this unconformity and that one. And Megan and Aaron are working on the this surface, the one that corresponds with that. And so we'll have a volume for the bottom 2 units also. The thing, Norbert, is we won't be able to tell you how much ice arrived. What we'll be able to tell you is how much ice is left. Right,
Sure.
because after each of these, there was these massive erosional periods. And so what I can tell you is the net of each of these units, but not the accumulation total, because some of it was lost.
Sure. And so what is the first volume? You know, how big is that volume?
I have it, it's published. I can go back to my 2016 paper. I don't have it on the top of my head. But I actually have that up, so I might better tell you because I know. Oh yeah, it's 0.6 meters global equivalent is what it is.
Okay.
So it's 80,000 cubic kilometers. Although I think that's an upper estimate. I think it should be a little bit smaller because what I was mapping back in 2016 included probably a little bit more than it should have. So that upper unit, yeah, I would say that it's probably a little bit smaller than 80,000 cubic kilometers.
Okay.
Hey, Isaac,
Yeah.
does that include the South Pole mapping that was part of that paper? Or is this just north?
I think this is just the north. The south added another 10%.
Okay, this is great, Isaac.
Thanks.
Any final quick questions? Unfortunately, your Zoom host is gonna need to log off here shortly.
Of course. Thanks, Amanda.
So I gotta, we're gonna need to stop the recording here shortly, but if there's any other final quick questions, let's get them in.
You can make me host, of course.
Can I, and will that shift the recording to you?
I hope not. I hope it would stick with you.
Or you can end it?
You know, I'm happy to stick on. If you want to end the recording, there's no reason that we have to continue recording the questions and answers.
Okay,
If you make me host and leave, then I can stick around.
okay. Let me keep talking. I'm gonna figure this out.
Yeah. I don't have a lot to say. Alan, this actually gets, oh, the thickness. Yeah, so the thickness in a lot of these places, going back to Alan's question, is around 100.